Hello, greetings, my friends. Good morning, good afternoon, wherever you happen to be around the world. This is Dr. Mohammed Nizami coming to you from Jerash, Jordan. This is part six of my RF sampled, direct RF sampled radio frequency receivers system design. If you're watching this for the first time, please go ahead and go back. If you could log into my channel, this is my YouTube channel, excuse me. And please subscribe as I um, need the subscription as a way to get encouraged to continue. The first five parts are listed here. So in case if this is the first time you're coming in to watch it, please go ahead and see if you can scan through the first five parts. This is integrated effort, so you will be missing a lot if you've done that. So, okay, this is, well, I mentioned this before. This is my uh, YouTube channel address, so go ahead and reach into that. Also, I have an outsourcing out of system and circuit design services. If you'd like to utilize my expertise, please reach out to me at this phone number here or this email right here. Now, I work with you from concept to basically BCBA fab files, anything from DC to 35 gigahertz using BC boards out of board level designs. Okay. All right. So we've been talking about these various parts of the of overviewing and illustrating the utilization of RF sampling analog to digital converters into RF sampling receivers that do not use any frequency translations, meaning, like I mentioned in here, RF to bits, basically. That's really the trend. So, and that's starting to be feasible because there is several companies right now, Texas Instruments, Analog Devices, um, Teledyne or E2V, they all have brought out tens of gigasamples per second devices that integrate part of the standard digital signal processing blocks like digital down converters and decimation filtering and so on. Okay, so as let's me see, let me put this in a this. So this is the block diagram I have been using. Basically, we've got an RF signal that comes into the antenna, and then we all we have is just a high-speed A to D that basically samples an RF signal that has been only amplified and filtered. And this block diagram is only for illustration, so we could have filters in here and filters in here and a few more stages and so on. But usually it's made up of low noise amplifier in the front end, some pre-selection filtering shaping, and then a variable gain amplifier, okay? Or voltage controlled gain amplifier that drives the A to D, okay? And then of course we have the FPGA or ASIC. Now, the previously, like say 10 years ago, the ADC didn't include a whole lot of functions other than just basically putting um, in bits corresponding to voltage level. But nowadays, really, a lot of the functions that used to be in the FPGAs have actually been included in the analog digital converter. So therefore, the for these gigasamples per second, the tremendously oversampling converters, the serial interface between the DSP platform and the A to D chip has been reduced further by including the decimation and frequency translation to the ADD, as we have shown previously with devices that are offered from Texas Instruments and analog devices and so on. So now the ADD, like I said, as you can see in here, really, it's not anymore just an ADD. It could be two or quad or 16 channels even, they have them. Not only this, but the ADD itself is actually interleaved ADC, which means um, it's a technique to speed up the conversion. And we have talked about this a little bit, and we'll talk about this in the coming sessions because there are some impairments due to this technique, which has to do with the interleaver spurs and harmonics. And so we have the frequency translation here. We have numerical controlled oscillator and NCOs here to drive and rotate the frequency. And then we have the decimator filtering, which reduces the bit rate so that when we go to the serial interface, the GSED 2004 B or C, now we have a much lower, more manageable speed on these buses. So these functions right now, they're really implemented in here, and you can see that we have analog digital converter core, okay, and then we have an NCO with mixer, okay, right here. And then we have a low pass filtering, okay, and a decimation. Okay, and the decimation is necessarily because when we oversample the signal with tens of gigasamples per second to overcome the filtering hardship of images and nearby interferences. But once we're past that, we really don't need to have so many samples. So once we rotate to baseband and we filter, we can just reduce the signal bandwidth to the appropriate bandwidth that has to do with the symbol rate, okay? And of course, you have the GSIT 2004 to 204 B or C, and that's your high-speed serializer that puts out the data out to the FPGA, as is shown in here. Okay, last time we have covered this, and we said let's zoom in on the ADD and just analyze this and look at this in more details. And we showed that the ADD input level, basically from full scale, all ones in here, to the quantization level, which is the least significant bit representable by the chip, which depends on the number of bits. Okay. And then we said we went and defined the spurious-free dynamic range and the signal-to-noise ratio. Now, of course, that can be defined relative to the full scale or relative to the carrier level, in this case, which is the desired component in here. And so far, we haven't talked about any issues like harmonics or like interleaver spurs. So this is just a standard classical ADD dynamic performance. And we said, how we're gonna design the chain in here, how we're gonna budget this chain, the budget link design of the system that is between the antenna and the ADD. And that depends on the ADD. Of course, we have to get from the data sheet some parameters and get parameters on the signal, and therefore we can actually do what's in between. And we developed these equations in here. And these equations, basically, the first equation was that the signal-to-noise ratio due to quantization is really always represented by the number of bits multiplied by 6 and add 1.763. Okay? So if you have 10 bits in here, that's 60 dB SNR plus almost 1.7, say 2, for instance. That's 62 dB SNR due to quantization. Of course, we said back then that the SNR is the parallel combination of three things, three sources of noise. One is this one here, the quantization, but we also have the thermal noise and we have the jitter noise. Okay, and we did define those and showed some examples how you compute that. So when you do this now, so if we go to here, then that means we know how far is the quantization below the full scale. So therefore, we can compute this noise level in here, okay, which is the quantization noise level. And that will be the background noise of this device in here, which means that whatever signal comes on the antenna, it has to be above that, or otherwise it doesn't do you no good. You won't be able to see it. So therefore, automatically right away you can see that you can size up the gain of this overall gain of this whole thing in here. Okay. And of course, we did define from the last sessions that even though the quantization level is here, but what we do is we bring up the thermal noise from the front end so that we're at least above this by a margin, which is either 10, 15, sometimes 16 dB, and we will show numerical examples today on how we do that. And once you do that, now the signal to noise ratio is defined, the lower side that defines the uh, the uh, the signal to noise ratio of the ADD is really not anymore quantization node, but rather the thermal noise. Of course, the thermal noise of this chain in here is really dependent on the gain in here and dependent on the noise figure, the cumulative noise figure in here. Okay? So the noise of the ADC due to just the quantization noise, which is the noise floor of the ADD due to quantization, is really the full scale minus the SNR of the ADD, which is defined by this. So that gives you this value in here. How many dBms in here? And then, of course, the really the ADD noise in here due to thermal noise on the front end is defined as minus 174 dBm per hertz. We add to that the integrate over the bandwidth of this whole system in here. We add to it the noise figure because the noise figure, remember, is does amplify the signal, and then we add the gain as well. Okay. And then, of course, now this here will be really the thermal noise. But uh, so the signal that we need, that is the minimum signal level that you can see, which is the receiver sensitivity of the front end, all you need to do is just add SNR required. So meaning, so what we do is we get the noise, thermal noise above this, and then we add all the factors that affect the thermal noise. And then we add on top of that, we have to amplify the signal by a certain margin so we can accommodate the demodulator, because the demodulator in here says, I want my signal to noise ratio, for instance, for a QAM signal to be 15 dB, and so on. Now, of course, likewise, this is the minimum detectable signal, but the maximum detectable signal is always going to be the top ceiling of the dynamic range that will prohibit the ADD from clipping, and therefore that is really the full scale. We just go below that by the peak to average ratio and then subtract 1 dB. And that's basically in here. So what we're saying is we want the ADD, the maximum signal that we can get in here, and that's because a lot of times that's because we're nearing the transmitter, so we're picking a large signal, or there is a large interference. Either way, so that value in here we need to have it not to exceed the full scale by a certain magnitude, which is the peak to average ratio and 1 dB. Okay, add to that. All right, so let's take a little illustration of the dynamics of this front end in here. So let's assume that we have an ADD and a signal which has a peak to average ratio of 8 dB that we're trying to pick. And of course, the full scale of the ADD, we're saying that is plus 5 dBm. Okay, so that's what defines this here. Okay, that's the all ones condition for the ADD. Okay. And let's say that we're trying to basically receive a signal which is minus 90 dBm, and the noise floor, thermal noise floor, is minus 104 dBm. That's at the antenna on this side here. So, and hypothetically, I had 3 stages one stage in here, which has noise figure of 1 dB, which is the LNA, and 25.5 dB. We have a filter which has a loss of a half dB, another identical stage to this here, and another identical stage to that. Remember, we don't have any frequency translation here, so everything you see, we can repeat it over and over. And then we have a variable gain amplifier in here, which can vary, the gain can vary from 0 to 35 dB. Okay? So let's see how, let's trace the signal and noise level along as it propagates from the antenna connection to the ADD. Okay? First of all, if you look at this, the maximum gain that you may have in here is really, you've got 50 dB from these two, and you've got 35, so that's 85. That's the maximum gain. The minimum gain is when this is set to 0. In real life, really, we might have even an amplifier that actually can attenuate. So meaning we can get the gains to be down, say, from minus 20 dB to plus whatever dBs. The minimum gain would be just these two stages minus these losses, and that would be 50 dB. Okay, so automatically from these two in here, we know what the minimum and maximum signal levels that we might have at the ADD. And I'm assuming I'm looking at the carrier in here, it's just a CW. Okay, and this is, of course, would be the x-axis of frequency of scaling. And I was just looking at the spectral strength of this CW along with the noise floor. First thing we do is minus 104 will come in here and gain by 25.5 and will increase by that much, or by the overall noise figure of this. And so we can see that the progression of how the signal comes in, where we get at the ADD, the minus 90 dBm will be minus 5 dBm. Okay? And when it's minus 5 dBm, that means the full scale is 5 dBm. So we're really 10 dB full scale, below that full scale, driving the ADD at minus 5 dBm. So it's minus 5 dBm, but it is also minus 10 dB full scale. Okay? And likewise, the noise floor is going to gain actually by the overall gain plus the noise figure of the system. Okay? So the minus 90 dBm is going to be add to that is the 85 dB gain, which is going to be basically minus 5 dBm. And the noise is minus 174 dBm per hertz plus the 10 log of the bandwidth. And the bandwidth in this case, let me see, I didn't specify it in here. But anyway, I assumed it's minus 104 dBm, so I must have predefined that in here. Okay, and we add the overall receiver gain and the noise figure. That would be the ADD, the noise, thermal noise right at this point. Of course, the antenna reference noise at the input in here is just the NSD plus 10 log of the bandwidth, okay? And the bandwidth, we define that to be equal to the bandwidth of this here, which is 10 megahertz. Now, of course, this is for thermal noise. We don't have any large signal presence due to interference or blockers. Blockers meaning it could be a desired signal, but very high level signal. So let's look at what happens when we add an interference, and the interference in here, or blocker, is minus 70 dBm, while the signal itself is minus 90 dBm. And we still have the same noise floor like we do have in here, okay? So when you look at this, as you can see here, that right away that we're going to have an issue because this signal is so large. If you max out this variable gain amplifier in here at the 35 dB, the signal when you get to here is minus 5 dBm, but the interference is plus 15 dBm. And this 80 dB, of course, the full scale, which at point that above that we're going to clip, is really plus 5 dBm. And you can see here it's plus 15 dBm. So right away you can see that this ADC will be in saturation. And that's assuming that these signals in here, these active amplifiers, did not already clip and saturate, producing harmonics and tremendous noise level raise. Okay, so right away you can see that there is an issue in here. So how can I detect this then? We need to reduce this interference. Of course, we can't reject this because, as you know, this is in-band interference. We're doing direct sampling, and this is one of the issues that you deal with when you're doing direct RF sampling because you don't have a frequency translation. If I had frequency translation, as soon as I mix with an LO, this here will move away from this, from the desired signal, and I will be able to reject it in the IF amplifiers, IF filters, ceramic filters at the IF stages or LC filters. So therefore, in here, really, I don't have any way of rejecting this interference, strong interference, other than having to use an ADD that it has a wide dynamic range that will enable me to see large signal and then very small signal. Okay. Like for instance, in here, if you reduce this, if you reduce this to -5, that means your gain has to be reduced by 20 dB. That means this has to go down um, to 15 dB. At that point, then this signal in here went down, and therefore the SNR went down. Okay, and which means also that if you want to do that, you're gonna very soon you're gonna have to there is so much signal range that you're not going to be able to see at the lower end because you're trying to accommodate the top end. Okay. So let's look at another example of how we budget the ADD issues with this signal without the interference. We in the coming lectures, we're going to look more at we're going to come back to this and say, for instance, we're going to have, because of the aliasing of both the noise from the aliasing, because we're oversampling a signal that is beyond the Nyquist frequency. So we're going to get some aliasing of harmonics and the harmonic creation by the ADD or the amplifiers front end. And we're going to have more issues has to do with the ADD in terms of spurs and harmonics, second harmonic and third harmonic of the signal, plus the inner lever spurs and the sampling frequency spurs, and that's going to complicate this scenario even more. For right now, we're not looking at that. We're saying the ADD doesn't have any of these impairments, but next sessions we're going to start to include that because that's really realistically the ADD that you're going to be using is an interleaved ADD, so it will have these issues anyway. And of course, because the the um, the Nyquist frequency is so wide that you fold back the noise floor additive white Gaussian noise from the different aliases and the harmonics as well. But let's look at this again with this example in here. Let's say that we have this example with these parameters. Here's our receiver. The first thing we will do is that uh, the full scale of this ADD, we're saying it's 9 dBm, okay? And we're saying that the signal to noise ratio is 72.5 dB. That's either from the 6 times the number of bits plus 1.76 dB or from the data sheet. So once we get this and we got that, we know exactly where the noise floor of the due to quantization will be. And in this case, it's 9 dB minus the 72.5 dB, which is going to put you at minus 63.5 dBm. What this is saying is that it doesn't matter what you have in the front end, the minimum you can see is going to be minus 63.5 dBm from the ADD without any additional amplification. Okay, so if you were to put this ADD directly to the antenna, the minimum you can see, okay, is the quantization noise, which is at minus 63.5. Now, realistically, now what we do, so that's good. So we have the noise, the quantization noise level is at that. But realistically, really, what we need to do, we need always to have the thermal noise come up at least say 10 dB above the quantization noise, which means if you subtract minus 63.5 dBm will give you raised to minus 53.5 dBm. So this here is where our noise floor of the entire system without any amplification, of course. But of course, now this signal in here, this is the noise floor. We need to be, for a realistic signal, let's say that we have a signal in here. That signal, we need to have some kind of noise, signal to noise ratio, meaning the signal, the desired signal has to be above this by a certain level. And in this case, I said 10 dB. So we have to raise that to 10 dB. So meaning now the minimum detectable signal by this ADD or this receiver is really going to be whatever level is, it needs to add up to minus 43 dBm. So minus 43 dBm is really the signal to noise ratio magnitude on top of the 10 dB margin from the quantization noise. So we have the quantization noise first, which is the SNR from full scale, okay? And then we add 10 dB above that so that where we want our broad background, the thermal noise, to be placed. And I'm going to come back to this in a moment. So, and then of course, on top of this, we have to have a certain magnitude of signal level to be able to demodulate, which is the signal to noise ratio, say 10 dB, for instance, and that puts you right at minus 43 dBm. Now, likewise, the other side, the strongest signal that we can tolerate will be this. We have the 9 dBm. We need to go down by the peak to average power ratio plus 1 dB. That 1 dB will always throw it in there. Everybody throws it in there as a margin. So we're really 9 dB below the 9 dBm. So that puts you at 0 dBm. Okay? So now, then in that case, what I have is from 0 dBm to minus 43, which is 43 dB, is really the dynamic range that I have with this system. So to do this now, what that means is that the total amplification in the front end is as follows. Now, I start out at minus 174 dBm per hertz, that's the NSD. In 10 megahertz, I'm raised to minus 104 dBm. In this case, I said 2 dB is the noise figure, so go up by 2 dB, which is your broad background is going to be amplified by 2 dB. So you're at minus 102 dBm. This is your noise floor. On top of this is going to be a signal level. This signal level, we said that the minimum level that I would need here is to get this raised so that I'm at least 10 dB above the thermal noise level, and which is above the quantization level by another 10 dB. So these two here really, that shows us the maximum and minimum gain that we need. The minimum gain comes from here because I need my noise floor, the thermal noise, equivalent noise in the front end. I need that to be raised at the ADD input so that it overwhelms the quantization noise of the ADD by 10 dB. So that means minus 102 plus the minimum gain on the front end in here to be at minus 53 dBm, which solves, if you solve for GRMN, that means 48 dB. So then the overall noise gain of the whole front has to be at least 48.5 or say 50 dB. Okay? Now that's including the variable gain amplifier. Okay? So that would be the maximum gain. Now likewise, if there is a strong signal in here, this signal in here, I want to make sure that that signal can never reach anywhere near 0 dBm. So meaning the maximum signal plus the gain of this thing in here has to be less or equal 0 dBm. Okay, and in this case, of course, or in this case in here, that's the minimum detectable signal in here. But there's another level, which means you have to go up here, and that means it turns out that you need to reduce the gain. So that's where this AGC sometimes needs to have to attenuate as well. Okay, so as you can see here, this is how you budget, manipulate the noise and the quantization noise, the thermal noise, and the minimum and maximum signal level that you're trying to detect, along with the characteristics of the ADD in terms of signal to noise ratio, number of bits, okay, and the sampling frequency as well. Now, let's take another example. Here's another example. We're saying that we have an ADD, which is 14 bits, and we have the full scale 1 volt peak to peak. We have the minimum signal that we're trying to detect is minus 1 or 2, and the maximum level is minus 15 dBm. Could be desired signal or blocker or interference that is coming at minus 15 dBm. And then we're assuming that we want 9 dB of SNR minimum, and the peak to average ratio is 5 dB. Okay? The first thing from these things in here is evident. We need to, so we have a full scale, which is 1 dBm, okay? And that basically convert the 1 volt peak to peak, and then to RMS, and then from RMS you compute the power, and then compute the power in terms of dBm relative to 1 milliwatt. So we've got 1 dBm is the full scale of the ADD. Now, the signal to noise ratio due to quantization is either from the data sheet, or you can just theoretically compute it using this 6 times 14 bits plus 1.76 to 86. So automatically now I have the full scale of the ADD, and I have the signal to noise ratio. So I'm going to go down from 1 dBm all the way by 86 dB, and that's going to take me down to minus 85 dBm. This is my quantization noise floor, okay? And so what I'm going to do next is make sure that the minimum gain of the front end, it has to raise the front end noise, which I'm going to show you in a minute, which is here. We have the thermal noise has to be raising up by 16 dB in this case. I'm saying that the margin is 16 dB. In here, I use 10 dB, okay? Okay, so 10, 15, it depends on you, how many fractions of a dB you want the deterioration, the SNR, due to this fact that you're doing here. And then on top of this, I have to be up by the 9 dB, which is signal to noise ratio. So therefore, my minimum detectable signal is minus 60 dBm. Now, but I said to here, I said I want my minimum signal to be at minus 102 dBm, which is this one in here, minus 102 dBm. Then what I want is this signal in here, the minimum, it has to raise up to this level, which is 16 dB above the quantization noise of the ADD, and then 9 dB of signal to noise ratio strength, so that my decoder, my demodulator, or my synchronization algorithms for tracking and acquiring, it has to fulfill that. So I have to be at minus 60 dBm. If that's the case, then minus 60 dBm, that's the overall gain of the front end of the receiver, which means my maximum gain is really minus 60 dB minus 102 dB, and that gives me 42 dB. Okay, so that right away puts the budgets the front end overall gain of the receiver. Likewise, the strongest signal, I have minus 15 dBm, which I said in here. I want it to cope with minus 15 dBm. Well, that here, with the gain of the receiver, it cannot exceed minus 5 dBm, which is the margin that I took by going down below the full scale by the peak to average ratio and 1 dB, which is 6 dB. And of course, you're at 1, that puts you at minus 5 dBm. So minus 5 dB, minus 50, that means the maximum gain is 10 dB, which says that really your receiver in the front end has to have a variable gain between 42 to 10 dB. Okay? So that's your dynamic range as well. So that then puts the overall receiver in here. And then, of course, you have to go further down. You don't have frequency translation, of course. That's the beauty of this. So you go ahead and distribute your gains and filtering according to the criteria which we're going to cover in the next section in terms of these filters, how we're going to distribute them. Okay, so now likewise, now we could look at this here. We didn't mention anything about the noise floor other than saying we need the noise floor to be to come to above 16 dB above the quantization noise, and that's because this here. So I have this is minus 174 dBm per hertz at room temperature. When you integrate over the bandwidth, that's basically minus 174 dBm per hertz plus 10 log of the bandwidth. And of course, that's going to be risen by the noise figure. Okay, so that I add the noise figure. And this would be my thermal noise right here. This thermal noise, you have to take it up to this level in here, which is 16 dB stronger than the minus 85. Okay, so that's another way of looking at it. Now, of course, this is the background. We know that the minimum signal in here has to be at least that much above it. Okay, 9 dB. Okay. All right. So let's now, so that points out to one fact that we are going to be basically, we're going to be going to the system view and going on, we're going to be actually looking at this and trying to trace the signals as they go through this chain in here, as you can see from the front end to the ADD in here, and we're going to trace out all these variations in the signal and noise level and interferences to be able to design the front end. This is a block diagram that shows the progression of the largest signal level that we're going to the antenna is going to pick up, that may pick up, and then we have the desired signal, and in this case put some numericals, okay, and then we have the noise floor. And so throughout these stages, now if you're in the old method of doing a single conversion heterodyne, for instance, in here, now notice that the blocker in here, okay, usually it has a certain distance away from the desired signal. So therefore, as soon as we go on the front end filter, it gets knocked down to a manageable level, okay? And then now what you have is you have the interference, you have your desired signal, and you have the noise floor. And you can see throughout this whole system how they progress. However, you can see that also the interference in here, because it has spatially located at a different frequency, at some offset away from the desired signal. So when your filter doesn't knock it completely, it's going to get amplified in the low noise amplifier. It's manageable level. And then what happens is it's going to go through the mixer. And right away in here, the blessing of this old heterodyne technique is that this interference is going to move further away from the desired signal and be completely eliminated, or will go down to a certain small level, either below the noise or close to the noise floor. Okay. Of course, if you don't have this, if you cross out this, you're doing direct RF sampling, in which case the interference is not going to go down past this point in here. It's going to keep rising, and it's actually going to be your top level, and it may overflow the ADD or clip the signal in here. So you can see that that's one trade-off that we have to try to cope with by utilizing the ADD that could accommodate with the dynamic range enough to accommodate the strongest signal and the weakest signal as well. So let's pick a few devices that I'm going to use in my system view illustration example in here. And this is a 28 gigahertz receiver, and this is an S-band receiver in here. You can see I use a transformer here to match between 50 ohm and 200 ohm. Okay, so we're gonna pick a few of these devices, and we're gonna stick to them using them in the coming sessions. So the first one, I picked this one here arbitrarily. to do the sub 6 gigahertz designs, this one and this one as well. Okay, so from two different manufacturers. This one's 14-bit, 3 gigasamples per second, and this one is 12 bits, 4 gigasamples per second. And I picked this is a display of the input to A to D relative to the full scale and showing the signal to noise ratio and the spurious-free dynamic range. Okay, for this, the same thing for this device in here. And we can look at these devices and utilize them in the illustration of the examples. For the 28 gigahertz one, I'm going to pick this device in here. I'm going to utilize this. And of course, these devices utilize, of course, the standard blocks that we now have been seeing, which is frequency digital translation, digital decimation, okay, and some other functions as well in there. So like in this one here, it has coarse and fine digital down conversion in it. So okay, and so is this one as well uses that. So we're going to go to these two examples, which I have shown previously. One is direct sampling 2.8 gigahertz, and we're going to go to 28 gigahertz. We're going to direct sample it, okay? And we're going to show in the coming sessions how we going to do the system design as well. So you can see that we're going to basically look at this. This here, in the next sessions, I'm going to utilize some of the Excel spreadsheets that people have wrote to actually compute this. And there are various sources that have these spreadsheets. I'll give you the links to them, and you can actually illustrate these in here. Or you can do it manually, just like I did it in here. Okay? All right, so I think we're done with this part. So I'm going to see you in the next parts. And we're going to try this time around, we're going to dig deep further into the ADD, and we're going to have to look at these specifications in here, which is the harmonic distortion. Let's see if it's mentioned in here. Maybe I didn't pick it in okay, here it is. The second order harmonic distortion and third order harmonic distortion. We're going to look at these, and we're going to look at the interleaver spurs due to sampling clocks and the number of interleavers. So we're going to see that, include those, and try to see how we can design the front end. We're going to do similar to this, except we're going to be utilizing the fact that we will have the ADD is going to pick up these harmonics and spurs. Okay, ladies and gentlemen, this is Dr. Mohammed Nizami. Thank you. Thank you. Have a great day, night, whatever it is. We'll see you in the next session. Thank you very much.